So the problem is to solve the given linear system of equations using the Gauss-Seidel method. So the three equations are 4x plus y minus 2z equals 0, negative x plus 5y plus 3z equals 18, and 12x minus 7y plus 25z equals 73. We're given the initial values 0, 0, 0 for x sub 0, y sub 0, and z sub 0. And we are told to keep iterating until we reach a tolerance of less than 1%. So the first thing to do is to check if your coefficient matrix is diagonally dominant. So how do we check for diagonal dominance? We get the elements from the main diagonals of each equation and compare their values to the other elements on the same row. So for the first equation, we have 4, and the sum of the coefficients of the other terms are 1, and the absolute value of negative 2, so 3. So 4 is greater than 3. And for the second equation, we have 5, and the sum of the absolute value of negative 1 and 3, which is 4. So 5 is greater than 4. And for the third equation, we have 25 compared to the sum of 12 and the absolute value of 7, which is 19. So 25 is greater than 7. So the values of the elements on the main diagonal are all greater than the sums of the absolute values of the other elements on the same row. So therefore, this system of linear equations is diagonally dominant. So the next step is to rewrite the equations, the first one in terms of x, the second one in terms of y, and the third one in terms of z. So now we have x is equal to negative y plus 2z over 4, y is equal to 18 plus x minus 3z over 5, and z is equal to 73 minus 12x plus 7y over 25. So for our first iteration, we're going to substitute the given initial values of 0, 0, 0 into our first equation, x is equal to negative y plus 2z over 4. So we have x is equal to negative 0 plus 2 times 0 over 4. Then we have x is equal to 0. And then we're going to write that in our table. So for the next one, we're going to substitute again the values into our second equation, y is equal to 18 plus x minus 3z over 5. So we have 18 plus, our x is still 0, minus 3 times our z is still 0 over 5. So therefore we get y is equal to 3.6. And for the next part, we substitute the most current values into our z equation. So now we have our x is still 0, but our y is already 3.6. And as we substitute, we always use the most recent values, the most current values into our equation. So therefore, we have z is equal to 73 minus 12 times 0 plus 7 times 3.6 over 25. Therefore, we have our z is equal to 3.928. So the next step is to get the relative error for each variable. So to get the relative error, it's just the new value minus the old one over the new value times 100. So for EY, we have 3.6 minus 0 over 3.6 times 100. So for EY, we have our relative error is equal to 100%. So we do that for all variables, and we check which one has the greatest error, and that will be our Emax. So we're just gonna keep iterating until our Emax is less than the specified tolerance. So for this problem, our specified tolerance is 1%. So after the 6th iteration, the lowest percent error is 0.83%, which is less than 1%. Therefore, our x, y, and z values are 1, 2, and 3 if we round these values up.
Solve using Jacobi method. So here is the problem. 4x minus y plus z equals 7. negative 4x plus 8y minus z equals 21, and 2x plus y plus 5z equals 15. We are to assume that the values of your x, y, and z at the 0th iteration is 0, 0, and 0. We substitute those values to our rewritten equations, which are these equations. So for the first iteration, your x would be 7 over 4, which is equal to 1.75. Your y would be equal to 21 over 8, which is equal to 2.625. And your z would be 15 over 5, which is 3. So here is the table for your iterations. We just keep plugging in these values to the rewritten equations in order to solve for the next set of iterations. We have to repeat this process until we achieve an absolute difference of 0.001. You will notice that at the 8th iteration, the absolute difference would be less than or equal to 0.001, and that approximating these values, you will get x is equal to 2, y is equal to 4, and z is equal to